Hello and welcome to this webinar on designing with developable surfaces in MAXSURF by Pat Couser. As an outline, first of all we will look at some background on the geometry of developable surfaces, and then we'll look at the workflow for modelling developable surfaces in MAXSURF. So first of all, some background on developable surfaces. So what is a developable surface? Well, it's a 3D surface which can be developed into a 2D plane without stretching or wrinkling. The mathematical definition is that everywhere on the surface the Gaussian curvature is zero. We'll look at the Gaussian curvature in the next slide, but essentially the Gaussian curvature is the product of the maximum and minimum curvatures at any point on the surface. It's also true that a developable surface is a subset of ruled surfaces, and these are surfaces which can be generated by sweeping a straight line along a curve. So a 3D surface is one which can be developed into a 2D plane without stretching or wrinkling, and here you can see a ship sample with a top side surface and a bottom surface which can be expanded and flattened out into a 2D plane. So what is a developable surface? So as we've mentioned already, a developable surface is a surface where everywhere on that surface the Gaussian curvature is zero. And the Gaussian curvature can be calculated at any point on a surface by first of all identifying that point and finding a tangent plane through the surface at that point. So at that tangent plane we have a normal vector, and then there are two planes that are normal to the tangent plane and go through that normal vector, which give you the principal curvatures, and that's where the radius of curvature is a maximum, and then at 90 degrees to that the radius of curvature is at a minimum. So these are the two principal curvatures, and if you multiply those together you get the Gaussian curvature, capital K. So we can use Gaussian curvature as a measure of developability of a surface. So a developable surface has zero Gaussian curvature everywhere, which essentially means that one or both of the principal curvatures are zero, i.e. the surface only has single curvature, so you can unroll it to form a flat plane without any wrinkling or stretching. And non-developable surfaces have non-zero Gaussian curvature, which can either be positive or negative, which basically means that both principal curvatures are non-zero, i.e. there's double curvature in that surface. And if we look at the bottom we can see three examples. The first is with negative curvature, which is sort of a saddle shape, where one curvature goes in one direction, one of the principal curvatures goes in one direction, and the other principal curvature in the other direction. So one is positive and one is negative, so when you multiply those together you get a negative Gaussian curvature. If you look at the middle example, one of the principal curvatures is zero, so this is a cylinder, and so when you multiply them both together you get zero Gaussian curvature, which means the surface is developable. And then if we look at the third example, like a globe or a football, both of the curvatures go in the same direction, so when you multiply them both together you get positive curvature. So ruled surfaces can be generated by tracing a ruling line between two edges, and here we have some examples. And developable surfaces are a subset of ruled surfaces, and they can be generated by sweeping a straight line along a curve. So we have a few examples here: a cylinder, for example, a flat plane obviously, and a cone. However, not all ruled surfaces are developable. Something like a helix, which is a ruling line that's moved along a helical generator, will produce a surface which is ruled but is not developable. So there's an additional constraint for a ruled surface to be developable. And this constraint is that the normal vectors at each end of the ruling line must be parallel, i.e. facing the same direction. So if we look at this example here, we have two edges to the surface, E1 and E2, and then a ruling line that joins those two together, a straight ruling line. If you take the tangent vectors at both of the points on the curves, T1 and T2, then if you take the cross product of those with the ruling line, you end up with two normals, M1 and N2, and if they're parallel, then that ruling line is describing a developable surface between those two edges. So why would we want to use developable surfaces to model a hull? Well, the main reason is that the 3D shapes can be formed by cutting out a 2D shape from a sheet of aluminium, for example, and then bending it into shape without having to do any stretching. And this makes it cheaper and easier to form the plates that go onto the hull. And that's really the principal reason for modelling with developable surfaces. So now we'll look in a little bit more detail at how we achieve this in MAXSURF. So the first thing to bear in mind is that MAXSURF does not automatically generate developable NURBS surfaces. It provides a lot of tools, but it doesn't actually generate the NURBS surfaces as developable surfaces automatically. So we'll look at how the developable surfaces are modelled in MAXSURF and then the workflow that we use for actually modelling these surfaces. So within MAXSURF, the ruled surface is defined by generator edges, and these are normally the longitudinal edges, but they could also be transversal vertical edges depending on the shape that's required. So I'll just outline the steps that are required, and then I'll show you in the application itself. So the first thing to do is basically to add one of the standard surfaces that we'll modify to produce the shape we're after, and in this case a buttock plane is quite a suitable one. The second thing is we then need to define that surface as a developable surface, and this will mean that the ruling lines will be calculated. We also need to make sure the ruling lines are actually displayed, so there's an option in the display menu for displaying the ruling lines. And then we want to add a number of control points and adjust the longitudinal stiffness of the surface so that we can create the shape that we're after. And here's a quick example of a finished ruled surface. You can see the yellow ruling lines between the two generator edges that have the control points on them.
So now we're going to look at how to design a developable surface. The first thing to do is to add a basic surface, and we're going to use a buttock plane in this case. So we can just rename it to this is going to be the top side surface of the vessel. And to be able to shape the vessel longitudinally, we need to add some control point columns. So doing this now, adding a number of control points along the length of the surface. And we can set them all to the same height of 2.5 meters. And we'll give them an offset just to get started of 2.5 meters as well. So we're going to make it a developable surface which will display the ruling lines between the two longitudinal edges, or the two generator edges, and we're going to give the longitudinal stiffness 5 to make it a smooth longitudinal curve. So now looking in the plan view, we can start to generate some shape to the two longitudinal generator curves, and you can see that the yellow ruling lines change as we manipulate the shape. So I'm just going to offset the bottom control points a bit as well. Again, we'll give them an offset of 2 meters. So you can get an idea in the plan view, and the profile view, and then the plan view. So now we're just going to carry on shaping the topside surface. And the idea is to get the shape that we're after, but also have a smooth distribution of the ruling lines. Ruling lines are actually in the developable surface that lies between the two generator edges. If we increase the precision, we get a few more ruling lines. So I'm just going to drag these control points to give a nice smooth shape. I'm doing this freehand, but if you had special constraints, you could add these as markers or enter numerical values as desired. So the ruling lines are calculated by looking at the normal of the two edges and the normal the tangent of the two edges, and the ruling line connects 2 points where the vector or the normal vector between the ruling line and the tangent to the generator edge are both parallel. So here you can see actually the ruling lines don't end at the surface, they actually go through the forward edge of the surface. Now if we wanted to make the forward edge of the surface straight, the ruling line has to end on the end of the surface, and we can do that by putting the 4 control points in the same plane. When we use the align to plane command, we have a couple of extra options to fix, to constrain the height or the longitudinal position, etc. So now you can see all 4 control points are in the same plane, and that means that the surface ends on the ruling line. It's always good practice to save your model as you go. Now we can do the same approach for the aft end of the surface by putting all 4 control points in the same plane. The first 3 define the plane, and then the 4th control point is moved to the plane. You can see now the ruling lines actually finish where the surface ends. So we can smoothen out these ruling lines a bit in the middle of the surface.
One thing that is often a desirable design feature is to have the end of the developable surface as a straight line. This basically means that one of the ruling lines have to end where the surface ends. On the left you can see the ruling lines follow, and then the last ruling line is coincident with the forward edge of the surface. And then on the right hand side you can see the ruling lines actually cross through the edge. This means that the actual developable surface wouldn't be straight if it was exactly developable. So how can we achieve this in MAXSURF Modeler? Well, recalling that for a ruled surface to be developable, the normal vectors at each end of the ruling lines must be parallel. And to do this, we need to get the last 2 control points on both edges to be in the same plane. So fortunately in MAXSURF we have a command align to plane, which uses the first 3 selected control points to define the plane, and here you can see them circled with the red circles. And then the 4th point, or any subsequent points, so just 1 point in this case with the blue square, will be aligned to that plane. And furthermore, if we want to apply any constraints, we can hold the shift key down when we use this command to give us some extra constraints. So once we've generated our ruled surface between the 2 edges, we then want to fit a NURBS surface to that ruled surface. So the first thing to do is to lock the edges, because remember that these edges are what define the ruled surface and we don't want to modify that. We can then generate markers to help visualize the ruled surface, and then the last stage is to fit the NURBS surface to those markers which define the ruled surface, and this can be done manually or using some of the automated fitting tools within MAXSURF Modeler. And just to remember, we cannot change the edges because they define the ruled surface. So looking in a bit more detail on how we fit the NURBS surface to the ruled surface, the first thing to do is to add control point rows, or maybe just a single control point row to the surface, so that we can adjust the internal part of the surface to fit the ruled surface. So adding the control point row, we have to go to the body plan view and then insert control point row as shown here. We then need to adjust the transverse stiffness of the surface, because previously it would have been linear. Now we've added a control point row, we can make it flexible, or if we'd added 2 control point rows, we could make it stiffness 4. So now we've added the control point row or rows, we can adjust the interior control points only. so that the NURBS surface matches the ruling lines. And if we've adjusted the ruled surface so that the end of the surface falls on a ruling line, then we won't want to adjust the control points that are in the transverse edges, those that I've highlighted in purple. And remember, we don't want to change the generator edges at all, so that leaves the control points that are just in the interior of the surface, those that are highlighted in red.
If we look at the rendering, we can do a false color render of the Gaussian curvature, which is a measure of the developability. Now, if the surface was all green, as you can see near the end, for instance, then the surfaces would be developable. But because there's twist in the surface, it isn't developable. So now what we're going to do is add some sections and waterlines along the length and depth of the model. This will help us generate a developable surface that matches the ruling lines between the two generator edges. So now I've got my waterlines and sections, and you can see these little crosses which cross the ruling lines are the points on the developable surface defined by the ruling lines that match the sections. And the green line is actually the section. You can see there's a difference between the NURBS surface and the developable surface. So what I need to do now is add a row of control points that I can use to adjust the interior shape of the NURBS surface to match that of the developable. So now I'm just straightening out the aft end of the control points just to give me a starting position to work from. So just continuing through, aligning all the control points for each column. Just finishing off with the bow. What I can do is generate markers where the ruling lines intersect the sections, the water lines, and if there are any buttocks. You can see a lot more ruling lines which can be hidden. Now we can see the marker points where the developable surface lies, and I need to adjust the NURBS surface by dragging the control points to match that developable surface. So we can do that in the body plan view for each of the sections. When the sections near the stern lie closer on top of each other, it becomes a bit harder. So I can do this as a manual process and determine how accurately I want to match. And in the markers menu, I can measure the error from the surface to the markers, and there we have 0.032, so 32 millimeters was the greatest error. Now looking in the plan view, I can use the stretch command for a long slender vessel. Helps me fit where the just expands the scale drawn on the screen. So now just doing a bit of manual fitting to some of the aft parts of the hull. So at this point I just want to change the internal control points. If I change the edges, it's going to change the developable surface and my markers will be incorrect. So I need to just change the position of the internal control points. So just doing the forward part here. Just pulling the surface out a little bit. It's always quite good to do this at reasonably high precision just to make sure everything's okay. So I can remeasure. Now we can see we've reduced by about a factor of 6 to 6 millimeters as the worst measurement just by a bit of manual manipulation. Now there's a command that we can use to fit surface to the markers, and we can specify a time limit. This uses a genetic algorithm, just so you have to make sure that the edges are locked. Just stepping through that took about 20 minutes. If you click on accept and close, this will give us the new surface, and again I can measure the marker error and see if we've got any better. So there again we've reduced it down to 3 millimeters from 6 from the manual adjustment. So that gives a measure to the exact developable surface. You can see it's given quite a reasonable fit.
So often when we're designing a ship, there's a number of compromises that need to be met. And in this case, we're aiming for a developable surface for the construction constraints, but often there are other competing constraints that we might want to address. So MAXSURF allows you as the designer to determine the level of developability of the surface. So we can compromise the developability, i.e. cheaper construction, against maybe hydrostatic performance, i.e. improving the GZ curve or the stability perhaps. The hydrodynamic performance, so maybe calm water resistance, can be reduced by changing the hull slightly, which may impact on the developability of the surfaces. Or maybe there are geometric constraints, for example, to fit the engine into the engine room or some other constraint. So how do we check that how developable a surface is? Well, within MAXSURF Modeler we have the Gaussian curvature plot, but this is very sensitive to developability, and really it either says yes it's developable or no it's not developable. If it's 0 then it's developable, if it's anything other than 0 then you can say it's not developable, but it's very hard to say how much stretching or shrinking might be required on the plate when you actually form it. So a more practical measure is to measure the strain required to form the plate, and we can do that within MAXSURF structure. So basically if there's 0 strain, then we just need to bend the plate to fit it onto the frames to achieve the 3D shape we're after, and it's developable. If there is some strain in the plate, then it will require some stretching or some shrinking. So we can use the plate expansion tool in MAXSURF structure to expand the surfaces and see what strains will be achieved in the plate to get the 3D shape that we're after. So looking at the strain required to form the plate. So if there's 0 strain in the plate, then basically there's 0 Gaussian curvature, and it's a 2D plate that can be formed into the 3D shape just by bending. And that's that top example. If we have negative strain, which indicates negative Gaussian curvature, then there's some shrinking that's required. Sometimes this might just be a case of pulling the plate onto the frame and then welding it in place, and that might be sufficient. If there's too much required, then some other form of manufacturing may be required. And then the third case, where we have positive strain, is basically the plate must be stretched in the middle to form over the frames. And in this case, if the strain's too high, then there's the chance of tearing or rupture of the plate as you're trying to stretch it over the frames.
Sometimes the scaling on the Gaussian curvature tends to show it worse than it actually is. So if we reduce the scaling, you can see most of that surface is green, apart from maybe a little area in the bow, indicating that it's essentially a developable surface. The best way to test is actually to save that and open the model in structure, where we can define a plate and do a flattening of the plate and look at the strains. So I'm going to open that model, change the precision to highest precision, and generate a topside plate. Use all the default settings, and now calculate the plate. It's relatively quick to calculate. And now I can go to the part window and look at my plate and look at the girth differences. So I've got 1 millimeter girth difference between the edges, and then also look at the strain. So we can see, as expected, we've got a slight negative strain of about 0.07% in that forward bow area. So maybe if that was too great, we could adjust our surface if necessary.
So what is acceptable strain? Well, there's a lot of factors that affect this, principally the material properties and also the forming process that is being used. So if you've got positive strain, as I just mentioned, which is basically stretching the plate, there's a risk of tearing and necking and rupture and causing holes in the plate. And if there's negative strain, where you're sort of shrinking the plate onto the frames, then there's a risk of wrinkling because you've basically got too much material. There's a lot of literature on sheet metal fabrication, and what's often used in this domain is what's called a forming limit diagram or curve, sometimes abbreviated to FLD or FLC. And the forming limit diagram can be used to gain a better appreciation of how much strain might be acceptable in the plate. You can also use the strain as a guide based on previous experience. If you've already made some plates and you know that 1 or 2% of negative strain is acceptable, you can still pull the plate onto the frames. Then you know in a subsequent design, if you have that strain level, then it should all go together quite satisfactorily. So far we've looked at modelling a developable surface and adjusting the interior part of the NURBS surface to match the developable surface. But there are some alternatives we could use. For instance, we can use a combination of the intrinsically developable surfaces such as planes, cylinders and cones to generate our model. And here's a very simple model that uses several planes and cones to model a very simple barge. A second alternative is to use trimmed parts of intrinsically developable surfaces, and often this might be a cone. So here we made a very tall cone and just used the top part of the cone as the top sides of the vessel. Obviously you could build up of multiple cones. Notice the cone doesn't actually have to be a circular cone. All that needs to happen for the surface to be developable is for one row of the cone to go to a point, and then you can make any shape with the other control points. And here we've got a very simple example of a flat bottom boat with the top sides made from the trimmed part of a cone. So just to summarise some of the key points of this talk. First of all, developable surfaces have zero Gaussian curvature everywhere. And in MAXSURF Modeler, developable surfaces can be modelled first by defining the generator edges and making the ruling lines quite regular along those generator edges. And then by creating markers on the ruled surface, and finally adding control points to the interior of the NURBS surface so that we can make it match the developable surface. And finally, in MAXSURF structure, we can verify the developability of a surface by computing the plate strain, i.e. the strain that would be required to convert the 2D plate into the 3D surface that we've modelled. And that concludes our presentation. Thank you very much for your time.